Hey all, welcome back. We're getting there, right? We're marching through. So we have, again, just to kind of review the last few things that we talked about, we're talking about climate change policy in kind of big picture ways. We talked about adaptation, so just adjusting to new climate. We talked about mitigation, just kind of preventing future change. And then we entered the realm of geoengineering, right? So we talked about solar radiation management, lots of different ways to do that. But what we're going to talk about this time is probably the one that, pops into most people's minds. I have students, in my other classes where we don't talk about carbon quite as much. It's maybe, a week of lecture. They always say, well, can we just go take the carbon out of the atmosphere? And yes, as we'll see, that there's a lot of ways to do that. And the methodology is fairly complex. But we're going to go through some of the ways that we plan on doing carbon removal, ways that we can do it actively, right? So ways that the technology exists, and some things that might work into the future as well. So one thing that we haven't really gotten into so much is, although we did talk about this a little bit in the context of energy generation. So if you think about where CO2 is coming from, there's a couple of ways to think about how you would go after it, right? Well, there's CO2 in the atmosphere at large, right? I could look out my window and I can see a bunch of CO2, right? Out of every 1 million atmosphere molecules that I can see, 415 or 20 of them are CO2, right? Talked about CO2 concentration. So that's one kind of way to think about CO2. Another is, well, how the heck did it get into the atmosphere? And a large part of that is actually what we call point source pollution, right? So we have energy production facilities, particularly coal and oil. Or coal and gas, excuse me. We've got oil generally used for transportation. That's a little bit more difficult because they're not still, right? It's like, I drive my truck around, it emits CO2. Cement factories, places where we're cooking the CO2 off of limestone to create cement, which we use for nearly everything. Every construction project requires a fair amount of cement. So those are all point sources of CO2. One of the technologies that we're trying to kind of get into, and we'll see some of the reality behind this, but right now we'll talk about theory, is what we call carbon capture and sequestration. So it's generally abbreviated CCS, carbon capture and sequestration, or carbon capture and storage, pick your favorite acronym. So this, in theory, is actually pretty simple. So we can go to a point source of CO2, and we can essentially take that emission, the gas emissions, the vapors, the particulates, all of those things that are created, whether it's a coal-fired power plant or, again, a concrete factory or something like that. And we can take that emission and we can run them through a fluid that will act like a solvent. You might be familiar with this concept, but we're doing this here again with chemicals, right? So it's not water in this case. Where as those emissions go through, the CO2 is actually dissolved by the components in that fluid and then becomes part of that fluid, right? It's because it's a solvent. Then the rest of the emissions can go ahead and leave, which is largely, hopefully unharmful particles. Once we have this solvent, this fluid that has CO2 captured in it, well, that fluid costs money. And so we can actually then add heat to that fluid, and we can pull the CO2 out. So we can then liquefy the CO2. So now we essentially have concentrated CO2, right? Concentrated carbon, in a sense. And we can do a lot of different things with it. Generally, we take this liquefied CO2, and the most simple thing to do, and it potentially has some problems, is to actually drill a really deep well, maybe a couple of kilometers, maybe 2 or 3 kilometers, and we actually inject the liquefied CO2 into what we call a geologic reservoir. So some rocks that have pore spaces and things like that. And that CO2 will just kind of will over time absorb into the kind of surrounding rock. And so you've actually then taken fast carbon and put it back in the slow carbon cycle. One thing that's a little bit of I don't know, Well, we didn't talk a lot about oil extraction and engineering that goes behind oil, but one of the things that exists in the oil extraction process, because it's a fluid that lives within the pore spaces of rocks, is there's natural pressure. You can pull some amount out. But if you can inject a fluid into that oil reservoir, you can actually get what we call enhanced oil recovery. So actually liquefied CO2 has been used to do this a lot of places. We'll actually pump it into a hydrocarbon reservoir and use that to recover more hydrocarbons. Right? So it kind of defeats the purpose in a sense, but it does get rid of some carbon that would have otherwise been in the atmosphere, and that oil would have been, extracted from some other reservoir. So again, you can see that particular example is maybe not the best, but just sticking it underground and kind of forgetting about it seems to be pretty reasonable. There's a couple of other things that we can do. We can also take that CO2 and expose it to minerals that will react with it. Calcium oxide, which is also known as lime, right? So it's kind of one of the fundamental things of limestone. Limestone is made out of a mineral called calcite. So calcite is calcium carbonate, CaCO3. And you can see the only difference is actually a CO2 is added, right? And so this, in a really weird way, this is the product we get after kilning limestone to create concrete. We drive off that CO2. But if it's exposed to the atmosphere, it's really reactive and it will actually absorb CO2. So if we're collecting it, we can also expose it to some other chemicals and it will turn to stone. You can turn it back into essentially rock form. Then you can pile it up in your neighbor's yard, right? Or pile it up behind the garage or wherever you keep all your stuff you don't want your neighbors to see. Obviously, I'm joking. We could actually, once we have it in this form, we could use it as a building material, right? So you could use this stone form to maybe make cinder blocks or, masonry or paving materials. So it could turn into something useful that, again, is part of the slow carbon cycle. So that could be pretty good. So the biggest thing that happens with CCS as a problem is that it's crazy expensive. We've pumped a bunch of money into technology of companies promising they're going to do this. Not very many of them have shown very kind of successful attempts. And first of all, it's really expensive to do, right? So it requires a lot of money. It's easier just to obviously burn the coal and send it off into the atmosphere. But adding this entire system and this entire process of re-injecting it, it adds an incredible amount of cost. And if you as a power producing company, you're incentivized to do things, if the government incentivizes you to do this, then it can become sustainable. But this doesn't work in like free market capitalism, right? Because there's zero benefit to the company for doing this unless there's like financial repercussions for not doing this. So again, it kind of, in the next module, we'll start talking about some of these financial systems that we can build to help prevent climate change or help limit climate change. This would likely, to really work effectively, this would likely have to be something that's totally funded and run by the government. But obviously that's like a confliction of terms, right? So really run effectively and run by this kind of massive bureaucratic organization. But it does exist. So carbon capture and sequestration. Aforestation, this is the opposite of deforestation. So if you think about a tree is made out of wood, right? Wood is primarily cellulose, which is carbon. And so, again, one of the things that we've explored, particularly when we were talking about the carbon cycle, is how as trees grow, they consume carbon, right? So they're essentially a short-term carbon sink. Maybe, in best case scenario, you might have a tree, right, that contains an amount of carbon, and it might sit in that tree for, 300 years until that tree dies and decomposes, and then that carbon is essentially released into the atmosphere. So that's kind of thinking about it at the scale of a single plant. The worst case scenario for that single plant is that, we've got all this carbon stored in the tree, then the tree burns down, or a forest fire comes through and wipes out the entire forest. Now, all of that CO2 is immediately back into the atmosphere. So again, quick carbon. So when we're thinking about afforestation, that example that I just gave of a tree and the forest burning down, that's all very well and true. But going back and thinking about our famous Keeling curve, right? We talk about nearly every single week in this class, right? The CO2 kind of every year. One of the things that causes the reduction as CO2 is being consumed is land use change, right? We talked about that, and deforestation. So, not only are we adding carbon or adding CO2 to the atmosphere, but we're also reducing biomass, particularly in places like the rainforest, which we've already talked about in this kind of two session module. So if we were to think about it at that scale, where we're actually increasing the percentage of forest land or rebuilding large swaths of forest land, that can significantly increase the land biosphere's ability to suck up carbon on an annual basis. So, yes, planting lots and lots and lots of trees can do it, but they need to be essentially done in addition to the trees that we have, right? So if we could reforest huge swaths of the rainforest, or even kind of the central United States, kind of convert thousands of acres to forest land, that would actually increase the CO2 in the fast carbon cycle. So it could work. It's probably not like the silver bullet to all of this, but as I'm sure you've come to realize, the real solutions kind of involve almost everything that we've been talking about, right? All of these are little kind of pieces of machinery in this kind of giant system that we can use to hopefully address and reduce future climate change. The other thing I wanted to talk about, actually, I forgot to mention this, but I just peeked down at my notes here, is, yes, trees. The potential, though, is that they do burn down, right? Like you could have a forest fire. But actually, an interesting use. So wood that's actually used for lumber, right? So when we use trees for kind of three primary things, right? We turn them into dimensional lumber, like 2x4s and 4x4s. You have things that make the framework of your house. So wood that's used for that, generally, it consumes carbon. It's made out of carbon. It comes in your house and it's used as a building material, and your house is likely going to be there for some significant amount of time. We also use plywood, right? So the other thing that wood becomes is plywood, which is a little bit different process. Then also paper. Paper is essentially kind of much more ephemeral, but really the wood used in construction can be thought about as a carbon sink. So massive wood buildings going up, in a way, is truly a green building material. It's carbon sequestration in a sense.